Hello, and welcome to day 5 of learning ML from chatgpt. So let's get started. So please give me day 5's lesson on ML. Copy paste the lesson. What do we have today? So we have logistic regression. Nice. So logistic regression, I'm pretty sure, is just when you have a curved. Like linear regression is when both go up linearly, and I think logistic regression, like log, as you have in time complexity, I'm pretty sure it's curved, but I can't be 100% sure. Okay, so day 5, logistic regression. Today we'll introduce the concept of classification and explore logistic regression, which is widely used for binary and multi-class classification problems. We implement logistic regression using both TensorFlow and PyTorch. By the end of the lesson, you'll be able to classify handwritten digits using logistic regression. Concepts. Introduction to classification and logistic regression. What is classification? Classification is a type of supervised learning where the goal is to predict the discrete label or category for a given input. For example, classifying emails as spam and not spam, or or recognizing handwritten digits from an image. Binary classification when there's only 2 classes, multi-class classification, more than 2 classes. So, what is logistic regression? It's a statistical model used for binary classification tasks. It predicts the probability that a given input belongs to a certain class. Unlike linear regression, which predicts continuous values, linear regression predicts probabilities between 0 and 1 using a logistic function, a sigmoid. Mathematical representation. For binary classification, logistic regression predicts the probability P that the output is Y given the input features X. So probability is the output is 1 because it's either 1 or 0, or I'm not too sure on the math, but I don't need. Oops. My bad. This is sigmoid. So probability of y1 and the features is sigmoid of the weight times x plus bias. So this is what we get: the weight and bias from model training, and then the sigmoid function. Okay, I kind of get it. So multi-class classification, we extend logistic regression using the softmax function, which generalizes the sigmoid to multiple classes. This sigmoid, it's explains it here. Probability that the output is 1 given the input x. Okay. So probability that the output is 1 given the input x is equal to the sigmoid function of the weight times the input plus bias. Okay. So this function is used to convert the linear combination of inputs into a probability. So that's sigmoid function of z. What's z in this? Is that just a function? I'm going to assume so. It's 1 over 1 plus e to the power of minus z. Okay, I'll keep reading on and see if this makes more sense. Loss function, binary cross entropy. In logistic regression, we use the binary cross entropy loss, also known as log loss, to measure the performance of the model. It is defined as. Okay, I'm just going to abstract away all the math around this, and I'll just trust that sigmoid is just sigmoid and linear, just linear logistic regression and multi-class classification. Well, binary classification is what I'm going to say, and multi-class classification. So softmax function for multi-class classification, softmax function is used to convert the outputs into probabilities that sum to 1 for each class. Oh, okay. Let me just read this again. So, let me use binary classification. So probabilities between 0 and 1. And then binary classification predicts the probability P that output is 1. Okay. And then for multi-class, we just use the softmax function, which converts all these probabilities for all the different classes. Ah, I see. So this is what I could have used. Maybe could have used a softmax function. Like I made this. It was like it wasn't like that good of an application, but I made this neural net that. Well, I used TensorFlow, but a neural net that predicts the last letter of a 5-letter word, and it had a bunch of training data, and it had 87% accuracy, but it wasn't actually good because 25 over 26 times 100 is greater than 87. So, and that was just predicting whether or not it was an S or not. So I could have used this softmax function possibly to generalize this into the others and provide the best possible ones. So part 1, logistic regression with TensorFlow. So I think from now on I just use TensorFlow as I just find it easier to use and I just like the syntax more. So from now on I'll just ask it to only provide TensorFlow. We use the mnist dataset, a popular dataset of handwritten digits for this exercise. We'll load and pre-process the data. Okay, so here we're importing TensorFlow. We're also importing Keras datasets. So I assume this is just the built-in dataset mnist into Keras, TensorFlow's Keras library. Then we import numpys and p, so xtrain, ytrain. So mnist makes this really easy to just load the data. We're flattening the images and normalizing to the shape of 0, 1. And we're also reshaping xtrain. Keras utils to categorically. Converts the labels to one hot encoded ones. So this basically has is 1, you don't have a column for number. You have is 1, is 2, is 3, is 4, and then it's either a 1 or a 0. This is what one hot encoding because that's how computers can understand it. So we're converting both ytrain and ytest to the categorical numbers, and we have 10 classes because we have 10 different possible numbers. Again, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. So define the logistic regression model. So we have the sequential and we have dense layer. So this is what we used like in the linear regression one. So we have 10 units. The input shape is 741. Okay. What is 28 by 28? Let me see. I'm assuming it is 28 by 28. Yes, 784. And that's what we're having here. So activation softmax. So this is making it multi-class. The multi-class classification. Then we compile it using the optimized SGD. The loss we're using categorical cross entropy. So when there are 2 classes, more than 2 classes. Okay, whereas I swear I read categorical cross entropy. Okay. This is binary cross entropy. To measure performance of the model. Okay, I'm just going to assume that it's correct. But I won't go deep into the math because I haven't been taught this in school yet. But I know this is sum of, I think. And then from n, and when you come by 1, is it? And this is the average here. We're doing 1 over n. And we're just doing... I know that yi is the input and y hat I is the actual, I think. But yeah, I'll just trust the model at the minute. And metrics, So let's read. A dense layer with 10 output units, 1 for each digit, and the software application. The loss function is from multiclass. Okay. So output layer with 10, a dense layer with 10 output units. Tracks the accuracy of the model you're doing training. Okay. So then we train it, test loss, test accuracy equals model.evaluate, x test, y test, test accuracy. Okay, so I'll skip the PyTorch for now. As you can see, like, there's a lot more code that we have to implement in the PyTorch one, whereas it's just all abstracted away with TensorFlows. So I'm just gonna copy paste this, and I want to see the accuracy. So we have, oops, that's the wrong one. I'm also gonna ask ChatGPT how you would go about just using one and then feeding into this model. I need to make sure to add follow-up questions to ensure my understanding. Keep clicking the wrong one. And then the final one here. Okay, so it's saying, oh, did we add model.fit? That's actually the most important one, training the model. Yeah, we did. With 10 output units, 1 for each. And just ask it. So for the 10 output units, please just explain this in more detail. Make the explanation simple with no math involved. Okay, let's see what it says. I'm just going to carry on reading this bit. So we fit it with 10 epochs, batch size of 32, and we have the validation data of x test and y test. Okay, so this is really simple. Like, very few lines of code. Well, simple except for, well, simple, I'm saying, being like few lines of code, like compared to the PyTorch alternative. Okay, and then test loss, test accuracy, model.evaluate. Okay, and then compute loss and accuracy. So let's break it down. Dense layer, fully connected layer, every unit is connected. In this case, the units are future predictions. Okay, units 10 means the layer has 10 output neurons. Each neuron compares to. You pass an image of a digit through the model. Each of these 10 neurons will give a score indicated. Ah, okay. So then we just need to find the highest one of them. We'll give score. Okay. So input shape means expects the input of 748 pixels. This comes from fattening a 28 by 28 pixel image into an array. Okay, so we need to convert it into just 784 images. Like, computer doesn't just understand an image by itself. If we just have it 748 numbers, each representing like the color of the pixels, say, whether black or white, then it's much easier for it to understand. Softmax function converts the raw output scores from the 10 neurons into probabilities that add up to 100%. So after applying softmax, the model will give you 10 probabilities. Each probability tells you the chance the input image is a particular digit, 0 to 9. The digit with the highest probability is the model's prediction. Okay. When you pass a flattened image of a digit through then select calculate score for each image, then softmax converts these scores into probabilities. Finally, you pick the digit with the highest probabilities as the model's guess for what digit image presents. So let me just go back up to this. And okay, after this one, let's see. Assignment: classify handwriting and experiment with different habit parameters. Okay. Learning rate, batch size, and number of epochs. So let's do this assignment and experiment. First of all, I'm just going to run it. These libraries normally take. And the mnist dataset I expect to be quite large, as this is used with lots of characters, I think. Okay, just loading here. Now please add it. Create a piece of code, a section of code, or like just a piece of code that outputs one image at random from the y. Which one do we validate it against? Yeah, test. From the y test, x test, and then output the y, the result that the model outputs. Okay, and let's just finish running. Yep. And run this. Okay, it's going to take a while. We put 2 out of 10. I'm just going to paste the code here. So yeah, input 4. Okay, so I'm just going to read through. So we get a random integer from the shape of 0 to the index position at 0 of shape at -1. So we're just getting a random index of x test in the x test array, or like multi-dimensional array, but we're doing it at 0. So random image, x test at random image, true label. I'm just going to leave that out. Random image reshape, so we're reshaping it 28 by 28, which is what we need for the model to predict it. That's it. Yeah, it's run. So that's pretty accurate, so 91.5. I'm assuming that's 1. And predicting it to be a 7. And run again to get a clearer image. Okay, nice. So we can see that these are all being predicted correctly. 2, yep, so this is all correct. 8, so we see this is one of the cases where it doesn't output correctly. But it should have been an 8 and not a 5. 3. Okay, nice. So now let's fine tune the epochs. So that's going to be a lot of epochs. So I'm going to half the epochs and see how much worse the performance deteriorates by. Oh, it's not correct English grammar. Okay. So before it's 91.5%, and we'll see what this goes down to. Let's see. 91.5 before. Oh, it actually increases. That's surprising. When we decrease it. Okay. Okay, and where do we pass in the learning rate? Validation. I don't think we do. We're passing in batch size and epochs, but we're not passing in the learning rate. I don't think we are. Okay. Now I change batch size to 64. So you see, this actually halves the amount of ones it has to go through as we're increasing the batch size by 2, so it will decrease the amount of ones we have to go through. And let's see how much this deteriorates by. Okay, so this is actually still higher than when we had an epochs of 10, batch size of 32. So I'm going to try just going down to 16 batch sizes. The epochs 5. And as you can see, this is taking a lot longer, but so it's basically the same as what we did. We half the epochs, but we also have the batch size, but this is, we hatch the batch size, it means it takes longer. Like there's more batches. So basically, I reckon these will cancel out and we'll still get 91.5. And let's see if we do. So do we get 91.5? We actually increase. Okay, so I'm actually gonna go like this. And whilst I'm reading through the last of the lesson, this will run in the background. Okay. So, summary of day 5. Concepts covered. Logistic regression, sigmoid function, and softmax function. Binary cross-entropy and multi-class classification. Skills developed. Implementing logistic regression models using TensorFlow and PyTorch. Applying knowledge to classify handwritten data digits using the mnist dataset. Logistic regression is a foundational algorithm for classification tasks, and mastering its implementation in deep learning frameworks like TensorFlow and PyTorch is crucial for tackling more complex models in the future. So I'll just read through the PyTorch as it doesn't hurt, and we still got to wait for this, as we've only 7 out of 20. Okay, now let's implement logistic regression using PyTorch. So importing Torch, we're implementing neural net module, optimizers, and Torch input datasets and transformations. Okay, so transform. Transforms.compose, transforms to tensor, transforms.normalize. Hopefully it gives an explanation of this. To tensor, converts images to PyTorch tensors. Okay, that's nice. Normalizes the image to have a mean 0.5 and standard deviation 0.5. So standard deviation, so that is in the range of 0 to 1. Okay, train datasets.mnist root.data, train true, download true, transform, train loader. Okay, I'm just going to skip past this bit and get to the actual linear regression model. So super, so this is just calling the I think it's a parent class, logistic regression model, and self. Init, self.linear, unit linear. So we're having 784 input features. And the forward x equals s view. We're flattening the input to 28 by 28. That's just shape of it, -1, and return softmax. So this is when we're turning binary classification into the multi-class classification, where each different like possible output, like 0 to 9, like the probability of each one adds up to 100%. So model equals the logistic regression model. Then we're having the cross entropy loss. So this is the loss function that, like, basically this is crucial in training the model. Optimizer, SGD, like we used with TensorFlow, and we have for the linear regression model, and this is learning rate. So we can see we're actually passing in the learning rate here, as compared to TensorFlow, which has abstracted that way. But I'm pretty sure you'll be able to do it somewhere as an extra parameter. So it combines log softmax and NL loss in a single class, providing an efficient way to compute the cross entropy loss. Training the model. So we're having 10 epochs, and for every input and labels in train loader, we do optimizer.0 grad outputs. This should be finished by now. It is. Let's see the output. Okay, like it hasn't changed accuracy much, so it looks like the cutoff point. I assume we maybe could get it higher if we had more and more epochs and batch sizes, but we didn't. So okay, because that would take a lot of time, and one of the things you got to factor in is the correct trade-off between time and how much percent of the data is correct. Okay, so that concludes. Wait, I'll just ask. Please now provide a code snippet that shows the model's learning the mnist dataset. Okay, it's going to do it from scratch. So just activation softmax, dense units 10, because we're having 10 units 0 to 9. Input shape, this is from 28 by 28. Image size that it was. Optimizer SGD, loss, classical cross entropy loss, and accuracy. But it's not actually. Okay, with a graph. Let's see if this will work. Yeah, so we are using matplotlib here. So I'm going to just copy paste this. I'm just going to add a title here that says print a random image and shows the prediction. Now fine. mnist dataset training with graph. chatgpt code animal. and we'll paste this in here and we'll run this. This will probably take a good chunk of time. Chapter 10 epochs. Just gonna see. So this history is modeled or fit. And we're doing the accuracy here, training accuracy, validation accuracy, title, training validation accuracy. So X label is epoch, Y label is accuracy, legend show, and this is loss, and then val loss. So training loss, validation loss, and then we're also doing epoch here, then but loss on the Y axis. So only 3 more epochs to go. And we'll see. Nine and 10. There we go. Now the graph should print. So we can see the accuracy improves up to epoch 8. I'm not sure why the well, it's to 9 because it's but it's 10 epoch. Okay. Then we can see that the loss keeps going down as the epochs increase. So yeah. And that will be the end of today's lesson, and stay tuned, and I'll see you in the next video for more, for the next machine learning lesson. So goodbye.